For this next video, we want to answer question 12 in chapter 2 from the study guide, how to prepare a buffer solution. This is an anserine buffer. First, we want to draw the titration curve for anserine, which is shown in figure 2.16, so it's this molecule here. And then we know that the isoelectric point of anserine is the pH where the net charge on the molecule is 0. So we need to discover the isoelectric point for anserine. And then the third part of this problem says, given a 0.1 molar solution of anserine stock at its isoelectric point, which is going to be the pH that we've calculated, and ready access to 0.1 molar HCl and 0.1 molar sodium hydroxide, and also distilled water, describe the preparation of 1 liter of 0.04 molar anserine buffer at pH 7.2. So we have a 3-step problem here. So let's look at what the titration curve looks like. So I've pulled up a titration curve for anserine, and you can see here that we have the 3 pKa's shown. We have pKa1 at 2.64. Oops, 2.64. We have pKa2 at 7.04 and pKa3 at 9.49. And you just have to look those numbers up. So those are our 3 pKa's. So let's see what those 3 pKa's mean. So if we are at low pH, so pH less than 2.64, then all 3 of the ionizable groups will be protonated. So those ionizable groups are the carboxylate group here, the imidazole group here, where this hydrogen is acidic, and the amine group here, where this hydrogen is acidic. So we can draw the reaction and the associated pKa. So the first ionizable group is this carboxylate group, and the pKa for that group is 2.64. So 2.64. So that if we draw the rest of this molecule as an R, we can say R COOH. So that's if it's not deprotonated. Sorry. Plus OH minus yields RCO minus, COO minus, plus H2O, and the pKa for that reaction, pKa1, is equal to 2.64. So at 2.64, half of the carboxylate group will be deprotonated. So remember, the Henderson-Hasselbalch equation, the pH is equal to the pKa plus the concentration of A minus over HA. Okay, and that's pKa1, okay? And that pKa is 2.64. So after we remove all of these ionizable hydrogens here, we are at this first equivalence point, and we begin to deprotonate the imidazole group at that point. So as we move up here into the curve, we begin deprotonating the imidazole group. So let's see what that looks like. So if we consider let's just erase all this crud here, getting in the way. So now we've deprotonated all of the carboxylate, and we're going to start deprotonating the imidazole group. So if we call the rest of this molecule R, then we can say R, and we've got the imidazole group. Okay. So we're starting out with it protonated. That's why it's acidic. And we're adding sodium hydroxide here. So we're adding equivalents, as we move to the right on this chart, of our strong base. So we can say sodium hydroxide, some strong base. And then we end up with, the R is connected here, okay, so now our nitrogen is neutral. And the pKa for this second reaction is 7.04. Okay, so we've gone from a +1 charge here to a neutral charge on the nitrogen, and when half of this one is deprotonated, so if we consider our Henderson-Hasselbalch equation for this pKa2, when half of this nitrogen is deprotonated and half is protonated, we're at pKa2, which is 7.04. And then when we've completely deprotonated all of this nitrogen, we're at this this second equivalence point. Okay, so here's our first equivalence point. Here's our second equivalence point. And our third equivalence point is going to be up here somewhere. Okay? Alright, and so once we've deprotonated all of these nitrogens here, let's go on down, all of this nitrogen here, then we're going to start deprotonating this amine group. Okay? So if we consider all the rest of this molecule to be R, then we can write this equation as NH3R plus OH minus yields NH2R plus H2O, and our pKa3 is equal to 9.49. So at 9.49, our amine group is half deprotonated. Okay, so our first part A was to draw the titration curve. So we're starting with a weak acid, and we're going to start at a low pH because it's an acid, and we're going to add equivalents of our base until we go through, as we go through our equivalence point. Now this is not a linear chart, this is a logarithmic chart. So we start at low and then we go through our first pKa and our first equivalence point, go through the second pKa and the second equivalence point, the third pKa and the third equivalence point. Okay, so let's look at this graph. So at a half equivalent we have the first of base, we have the first pKa. At one equivalent of base, we have our first equivalence point. That's where our first ionizable group is completely pulled off. At our second pKa, we have our second, it's also called a half equivalence point. That's where half of our second ionizable group is pulled off. Okay, so we have half the concentration of the nitrogen that has been deprotonated and half that has not. Then at our second equivalence point, we've pulled off all of these hydrogens on our second group, second ionizable group. At our third half equivalence point, we've pulled off half of the hydrogens from this amine. So we have half of equivalent of this and half an equivalent of this, and that's at our third equivalence point, which can be viewed here on the graph. It's right here. And our third half equivalence point, and at our third equivalence point we've pulled off all of them. Alright, so so that is how we would draw this titration curve. Now part B says, what is the isoelectric point? The isoelectric point is where this molecule is neutral, and this molecule will be neutral where, let's erase everything here. This molecule is neutral where we have a negative charge here. So we've got a negative charge here when we go through that first equivalence point, and then we're going to have these two positive charges. But when we've pulled off all of these, the hydrogens from the second ionizable group, okay, remember, when we pull off these hydrogens, this species becomes neutral. Okay, so this is no longer positively charged. This doesn't have a hydrogen here anymore. Let's see if we can get a white. Let's get a white. Alright, so this hydrogen is gone, and that group is now neutral. So what do we know? We know now that this oxygen has a negative charge, this NH3 has a positive charge, and this molecule overall then becomes neutral because the charges balance each other out. And so when this carboxylate group is negative, all of it, and all of the amine groups are positive, then we've reached the isoelectric point. And what point is that? That is at the second equivalence point when all of the imidazole nitrogen has been deprotonated. That is the second equivalence point here. So how can we calculate that second equivalence point? Well, that's the midpoint. That's the midpoint between these two half equivalence points. Okay, so how do we calculate a midpoint? Let's just go up here. How do we calculate a midpoint? A midpoint is our isoelectric point. So our Pi is equal to the second equivalence point. All right, and that's going to be equal to the midpoint between the third pKa and the second pKa. Okay, because realize that that is between halfway between 1.5 equivalents and 2.5 equivalents. So we want the pH at that midpoint between these two. All right, and so that is going to be the pH between these two midpoints is going to be 7.04. That's the pH at the first midpoint, plus 9.49. That's the pH at the second midpoint. I'm sorry, the second half equivalence point, divided by 2, and that'll give us the midpoint of 8.27. So the pH at the second equivalence point is 8.27 because it's the midpoint between these two half equivalence points. Okay, in the next video, we're going to do part 3, which is to calculate our buffer solution.